Thank you very much. Yes, I'm going to be talking about the Bluemira fusion power plant framework, and specifically I'm going to be showing an example of some Poloidal field coilset and divertor design. So what I'm going to be covering in this talk is first a little introduction into the work we do with power plant modeling and integration, overview of the Bluemira framework. I'll show an example of a design workflow with the step design, and then I'll talk a little bit more about the equilibrium optimization, coil set, and diverter design within that workflow. So first, an introduction to the group. Our objective is to address the challenge of fusion power plant design and integration. We have two codes. If you look at the figure on the right-hand side, you can see where they take up the space in terms of complexity and time. Our aims are to formalize and expedite the design cycle, to provide useful information for decision-making in fusion programs. Our codes are both open source, and they are either in Python or in some of the parts of process, Fortran wrapped Python. In a little bit more detail, process is our systems code that uses primarily 0D and 1D models. It's low fidelity, it's fast, and it's used to explore design space and generate an initial design point. Bluemira is medium fidelity models, 2D and 3D capability. It would typically take the process output design point as an input and then do more detailed optimization and design. Bluemira has a variety of different capabilities, so sorry for the sort of word bomb on this slide. We do optimization of parameterized CAD, we can integrate with external codes, look at that magnetostatics, balance of plant, remote maintenance, optimization of divertor, and then also in post-processing, we can look at neutronics as well. And an important thing is that all of these models are integrated and automated, the benefit of which is a self-consistent workflow. You can have different levels of fidelity at different stages in the design process. The expedition of these design activities for initial concepts mean that you save time, you can consider more options during your design phase, and you can also reduce the risk in your program. The figures on the bottom of this slide are just showing some of the CAD outputs. In the center, we've got the full fusion device design. On the right-hand side is a little close-up look at some remote maintenance ports that we were investigating. And then on the left-hand side, a close-up of a section of the divertor cassette. Right, this is an example of a workflow using Bluemira. This is for the step device, so spherical tokamak for energy production, but it could be for any device you wanted, and it's made up of various different Bluemira modules. Typically, you would start with an input. So in this case, everyone starts with an input. Sorry, typically our input would consist of a process output, some sort of result from a transport solver. So we have Gesso in this case, and then also config files where the user sets up the requirements and constraints for the device that you're designing. We take that information and we create a reference first steps for our free boundary equilibrium. And then we perform a series of optimizations of the coil sets. I'll talk a little bit more about that later in the talk. Once we've reached a termination condition that you specify, we then move on to the designers for the thermal shield, the first wall, breathing blanket, vacuum vessels, and then you can move on to post-processing where you consider things like first wall heat loads, magnetostatics, and neutronics. In terms of plasma equilibria and coil set design and optimization, like many codes, we are solving the equation. We're using a free boundary solver. The figure on the left-hand side just shows the setup for a demo-like device. So we've got our grid, plasma boundaries, and coil locations. The animation, which unfortunately I think isn't working unless it's been playing and I haven't noticed, shows poloidal flux surfaces and plasma during an optimization. So what we're doing here is iteratively optimizing the coil set currents and positions, and then resolving for the Grad-Chaffanoff for your plasma equilibrium. On the right-hand side are two outputs. We've got the poloidal cross-section of PF coils associated with the equilibria on the center, and then also a snapshot from our interactive CAD viewer showing those same coils, but in 3D. Okay, now I'm just going to show you an example of this PF coil and equilibria optimization within the STEP workflow. In particular, we have added some new Divertor objectives and some core constraints. So we wanted to be able to consider, as well as the space that Divertor is taking up and the effect that it has on the PF coil design, the heat flux that would be hitting the outer target. So you're constantly getting these particles and energy leaving the core region, moving into the region with open magnetic flux surfaces. And in a power plant relevant machine, that is a very high power that might exceed material limits. The way we've done this is using two classic geometric properties as a proxy for heat flux reduction on the targets. The first of which is for greater flux expansion, and the second of which is for greater connection length. These are shown in the cartoon figures here on the right. The first one showing the flowing out of flux surfaces, the flux expansion spreading out that heat load over the target, and the second showing an increased distance from the outer midpoint on that plasma to the target location. We've also implemented spherical harmonic constraints. So these constrain the coil set contribution in the field to the core region of closed flux surfaces. This is done with a set of spherical harmonic constraints, each of which have an amplitude or coefficient, which you can then constrain, allowing you to preserve the core region and keep it fixed while you're experimenting with different configurations for your divertor leg field. We have implemented these in the set of coil set and equilibria optimizations in the STEP workflow. So first we do a coil position and inner divertor optimization. We have maximizing flux expansion as the objective, but we also consider a number of constraints. So we have isoflux constraints on the core plasma and engineering constraints. We look at the coil force and coil field, as well as the maximum current. We then take the output of that and feed it into our outer divertor optimization. So we look at the connection length for the outer leg, and then we're using spherical harmonics to constrain that core. So first of all, the flux expansion optimization. The figure on the left-hand side shows the input coil positions. We are also optimizing for coil position during this particular phase, as well as the magnetic targets that we've set for the last closed flux surface and then the outer leg. The figure on the right-hand side shows the resulting plasma equilibrium, but I'm going to show you a zoomed-in close-up of the inner divertor leg. So you can see that we do get some flux expansion. The blue shows the input and the red shows after optimization. We are restricted though by the position limits for the coils, but we do get an increase in flux expansion of 10 to 20% along the target, which is not bad considering how tight that space is. The connection length optimization follows, where we're looking at the outer divertor leg. The figure on the right-hand side is showing the difference between the poloidal flux from your input equilibria and optimized equilibria. And in this particular case, we've used spherical harmonics, as I said before, to constrain the core. So you can see that there is basically no change in that core region. The last closed flux surfaces are sitting on top of each other, and the changes are where the coils are located for that outer leg optimization. So I'm just going to change slides. Okay. Oh yes, and I highlighted that with stars. That's nice. These are some more outputs. So following those two optimizations, so the figure on the left-hand side showing the Poloidal slice with the PF coils, the TF coils, and then a simple model of the blankets. And the figure on the right-hand side showing the modeled resulting first wall heat load. Okay. We've implemented some new Divertor objectives in the step workflow, and we can see the impacts on the design within minutes. At the end of the run, we get various different data and plots that are outputted, including CAD in various formats, slices of the different components, heat loads, and all the physics parameters that you want. And they can be used in design and integration activities. And I would also like to highlight our GitHub repository. Please go there if you would like to contact us, if you'd like to see our documentation. We have worked examples, and also if you haven't already, please go and look at the Bluemira posters. Thank you very much.
That's cool. Thank you, Georgina. So I don't see anything in the Q&A yet. So while people are thinking about their questions and typing them in, I'm going to ask one. So Bluemira is like one of the kind of leading examples of open source software coming out of UKAA. I'd say it's one of the sort of exemplars. How easy or difficult was it going through the process of being allowed to open source Bluemira and kind of getting agreement to be able to do that and implementing it and all that kind of stuff?
I am not going to be the best person to answer that question because I joined when it was already open source. I know that when I started, Process wasn't open source. That's our other systems code. Oh, sorry, I thought I saw a message. And I believe it took about a year to move from a non-open source code to an open source code, but there might be someone in the audience who'd be able to correct me.
Okay, that's cool. Well, in the meantime, we have had a question come through in the Q&A from Jonathan asking, are you able to compare and contrast with 3G Snake? So they use the Newton-Krylov solver for forward mode, gradual runoff. And yeah, he was just saying that he missed what the approach was in Bluemira.
Oh, yes, I'm sorry. We use a Picard iterator, and we would be interested in looking into other iterators as well. I haven't looked into a direct comparison. We've done previous comparisons with Fiesta as well, but definitely having a look at a comparison between 3D Snake and Bluemira is like one of the next things that we'd be looking into, as well as exploring different types of iterator as well. I will say that one of the benefits of using the spherical harmonic constraints is they do keep the core very fixed, so you don't have to resolve for the
Okay, if it might, hopefully it's not just me. Maybe we seem to be losing Georgina.
Can you hear me?
Oh, yeah, you're back.
Sorry about
that. Oh, okay, she seems to be recommencing. We've got a little bit of time, so I'll give her a few minutes, and there is another question waiting as well. So hopefully she'll reconnect in the next couple of seconds.
Sorry, I think I'm back again. Can you hear me?
Yeah, you're back. Brilliant. Missed the very end of that answer though, and you've got time, so feel free to.
At what point did I cut off? Sorry, if
good question. I'm not exactly sure how far it got. I was trying to pick up other questions in the chat.
I'll summarize. We haven't done a direct comparison yet. We are interested in doing a comparison. We use the Picard iterator. We have been exploring the idea of using other types of iterator. Using the spherical harmonics has the benefit of constraining the core well enough that you don't necessarily have to resolve for the Grad-Schaffner equation every time. I think that's a summary.
Cool, good. And we've got another question from Daljit. So I was asking, how does the Bluemira package complement IMAS? Is there a specific requirement from the public or private sector that the project is trying to address?
So to answer the first half of the question, I believe IMAS compatibility is something that so it's something that we're working on, but that it's basically on. I think James Cook would be the person in our team if you're interested in that to speak to. And what was the second half of that question?
So first of all, James has also very helpfully put something in the Q&A to address the IMAS questions. Thanks for that, James. And the second part was, are there any specific requirements from the public or private sector that the Bluemira project is aiming to address?
So in terms of what we're aiming to address is we are trying to create something that allows you to explore designs rapidly. That is the key part of Bluemira. It's very flexible. Like I said, you can make changes and look at the outputs and the design really quickly. To give an example of time, in terms of looking at PF coil sets, I can sometimes complete an investigation in like an afternoon. So it's very fast, and it also, because it's all fully integrated, I think it also significantly reduces the risk, especially when you have lots of different design teams for different components working together.
Brilliant, thank you. I will just summarize for the audience James's answer. It came up actually earlier on today that they're working on the part of their external EQ disk package for integrating with IMAS at the moment. Yeah, that was, and Daljit was saying thank you for the answer. That's cool.